Welcome back to our discussion on TCP and UDP. In part 2, we will see how TCP performs its functions of error recovery and flow control, and then we'll wrap up the discussion by comparing the headers of the two protocols. As we mentioned in part 1, TCP has the ability to perform error recovery of lost data. That makes TCP a reliable protocol. So let's look at the TCP communication process when there's no errors as our first example. So here, the client and server have already completed the three-way handshake and have established a session. They're now ready to actually communicate over TCP. Starting with step 1 and step 2, the client sends two segments of 1,000 bytes each to the server. So note, TCP does allow multiple segments to be sent at the same time. So here, the client is sending two segments of 1,000 bytes. The server receives these segments, and each of these segments has a sequence number. And for simplicity, I've made the sequence numbers 1,000 and 2,000, which matches the size of the segment. So in step 3, the server acknowledges the receipt of the two segments by sending an ACK, an acknowledgement. Now this ACK message from the server has the sequence number that it expects to see next. And since the server has seen sequence number 1,000 and 2,000, it expects that the next segment that it receives will have a sequence number of 3,000. So that's in the ACK that it sends. Now the client receives this ACK, and that's at the end of step 3. Then we get to step 4. In step 4 and in step 5, the client sends two more segments. Again, each of 1,000 bytes with the sequence numbers of 3,000 and 4,000. So the client knew the server received both its previous segments because it got the ACK back with the next expected sequence number of 3,000. So the client went ahead and sent two more segments with another 1,000 bytes each with sequence numbers 3,000 and 4,000. And this process would continue. As you see in step 6, the server, upon receipt of the next two segments, sends an acknowledgement back with a next expected sequence number of 5,000. So now let's look at what happens if there is an error, a segment is lost and has to be retransmitted. Again, we start with the three-way handshake being complete between the client and server. They're ready now to communicate over TCP. In this example, in steps 1, 2, and 3, the client is sending 3,000 bytes at a time using three segments of 1,000 bytes each. Now suppose, for some reason, the second segment doesn't arrive at the server. The server receives the first segment, sequence number 1,000. It doesn't get the second segment, but it does get the third with a sequence number of 3,000. So what the server is going to do is send an acknowledgement with what sequence number it expects to see next. And in this case, it's going to be 2,000 because it never received a segment with sequence number 2,000, so it knows it missed something. So it's letting the client know the next thing I need to see is a segment with sequence number 2,000, and that's in step 4. Step 5, the client receives this acknowledgement from the server, notices that the server wants to see a segment with sequence number 2,000, and so it retransmits that lost or dropped segment. Then in step 6, assuming it actually gets to the server this time, the server then sends an ACK with the next expected sequence number, which in this case is going to be 4,000, and the client will then send three more 1,000-byte segments. Another TCP function is to provide flow control. Now it does this with a process called windowing. The TCP send window is dynamic and can be made larger or smaller by the receiver to allow larger or smaller amounts of data to be sent by the client at one time. Basically what this is doing is the receiver's telling the sender, you can send more segments at once because they're getting here reliably, so let's maximize how much bandwidth we can use. Or the opposite could happen. If segments are being dropped, like we saw in the last example, the receiver could tell the client, let's make the window size smaller, send less data at once because this connection is not very reliable. So this is called windowing. So here we have the three-way handshake again complete between the client and the server. In step 1, the client sends a 1,000-byte segment with sequence number 1,000. In step 2, the server receives the segment and sends an ACK with the next expected sequence number of 2,000. And since that segment arrived reliably, the server can suggest a new size window, perhaps a size window of 4,000. This would tell the client that it can send 4,000 bytes at once. So in step 3, the client sends the next 4,000 bytes in 4 segments. If all are received by the server in step 4, it sends an ACK with the next expected sequence number of 6,000. So TCP can make the window size bigger to allow more segments to come through at once, but it can also make the window size smaller if segments are being lost in transmission. Again, this is the function of flow control, and the term we use to describe this is called windowing. Now, just as the TCP connection process was formalized with a 3-way handshake, the TCP termination is also formalized. And here's the steps in TCP connection termination. In step 1, the client sends a FIN message, in this example, sequence number X, to the server. In steps 2 and 3, the server sends 2 messages. It sends an ACK to the client's FIN with the sequence number X plus 1. That lets the client know that its FIN was received by the server. The server also sends its own FIN with a sequence number of Y to the client. In step 4, assuming the client received those messages from the server, it will send back to the server its own ACK with the server sequence number of Y plus 1, letting the server know that its FIN message was received. So after this 4-step process, both the server and the client have acknowledged each other's FIN messages, and the TCP connection is then formally terminated. So we'll wrap up our discussion on TCP and UDP by looking at the 2 protocol headers. Looking at the TCP header, note the sequence number, acknowledgement number, and window fields. These are the fields necessary to perform the reliability and flow control functions that we just discussed. Also notice we have source and destination ports. That's where the port numbers go. That's where the protocol port numbers are put. That's our layer 4 addressing used by TCP. Let's talk about UDP for a minute, and then we'll look at the UDP header. UDP is connectionless. It's not reliable, which means it cannot retransmit dropped segments. It does no windowing, so there's no flow control. There's no reordering and no segmentation. So UDP has much less overhead than TCP. That might seem undesirable, but it actually is very suitable for voice over IP, streaming video, streaming audio, and also domain name system functions. In other words, applications that don't need reliability, but rather just need sheer speed of transmitting segments. So here we see the UDP header, and think back to what the TCP header looked like. Here in comparison, the UDP header is much smaller and more streamlined, meaning it's going to have very little overhead. Not many bits are used to make up the UDP header. And notice it really mostly consists of just the source and destination port numbers, which are required for creating the sockets necessary for a session and for multiplexing.